Hello class, this week is week 15 and we will be talking about integer exponents, percentages, decimals, and ultimately talking about the rational, irrational, and real numbers. We begin with integer exponents. So let a be any number and n be any natural number. Now when I say natural number, this expression right here, this is of course referring to the counting numbers 1, 2, 3, 4, 5, etc. I'm not putting any restrictions on what a can represent though. We're going to say just any number. So it could be a fraction, a whole number, a negative number, a positive number, etc. Any kind of number we've talked about so far, a can be that. So when we have a situation where you have a raised to a power, remember that we call the a the base and then the n the power or the exponent. And when you have a raised to the n, it means to multiply a with itself n times. So there's a total of n a's in this list being multiplied. So like a cubed would be a times a times a. You'd multiply 3 copies of a. When you have a zero exponent, a to the 0, as long as a, the base, is not 0 itself, so any non-zero number raised to the 0, we're going to define to be equal to 1. And then when we have negative exponents, so if n is a counting number, then negative n, of course, is a negative counting number, or it's an integer. And if you have a to the negative n power, it means to do the reciprocal of the base. So do 1 over a, and then raise that to the nth power. Of course, that can also be interpreted as simply doing 1 over a raised to the n. We're going to do some examples of these ideas here below. Express each value in a new way. So 5 raised to the 3, or you can say 5 cubed. This means to multiply 5 with itself 3 times. So 5 times 5 times 5, and 5 times 5 is 25, times another 5 is 125. 5 raised to the 2, or you can say 5 squared, is just 5 times 5, and that gives us 25. 5 raised to the 1, or just simply 5 to the 1, is simply 5. So any base raised to the 1 is just going to be that base. 5 to the 0, that's by definition going to give us an answer of 1. 5 raised to the minus 1, so negative exponents. We have 5 raised to the minus 1. When you have a negative power, you instead do the reciprocal of the base, so we consider 1/5 instead of 5, and we do the positive version of that power. So we do 1/5 raised to the 1, and anything raised to the 1 is just itself, so we can just say 1/5. So in other words, when you see a number like 5 raised to the minus 1, it really just means do the reciprocal of that base. 5 to the minus 2 can be thought of as doing the reciprocal of 5, which is 1/5, and raising it to the positive 2, or squaring it. So that just means 1/5 times 1/5, and we know when you multiply fractions, you multiply the numerators and you multiply the denominators, so that gives us 1/25. You can also think of this as just doing 1 over 5 squared, so just squaring the 5, and that gives us that 25 in the denominator. And then finally 5 to the negative 3. This means to do 1/5 in parentheses and cube that, or you can also just do 1 over and cube only the 5. Some of you who already know properties about exponents know that if you have a fraction like a over b raised to a power, that power should, you should have each the numerator and denominator both be raised to that power. Technically that's happening here. We do 1 cubed, which is still just 1, and then we have 5 cubed down here. And 5 cubed is, of course, 125. We've already talked about that. So this is 1/125th. Similarly, with bases of 10, so 10 cubed is just 10 times 10 times 10, and that gives us 1,000. 10 squared is 10 times 10, which gives us 100. 10 to the first is just 10, and 10 to the 0 is 1. So you might notice something here. You can, when you do 10 raised to a whole number, the whole number indicates essentially how many zeros are going to be after a 1. So 10 to the 5th would be a 1 with 5 zeros after it, which is going to be 10,000. Something to think about. How about 10 to the negative powers? So 10 to the minus 1 means 1/10 to the positive 1, which is just 1/10. 10 to the minus 2 means 1/10, and then we're going to square that, which you could just simply do 1 over 10 squared. which is 1/100th. And finally, 10 to the negative 3 means 1/10 cubed, which is 1/10 cubed, which is 1/1000th. And a pattern you notice here is when you're doing negative powers on a base of -10, when you see 10 to the minus 2, it means to do 1 over and then a power of 10, and the number of zeros you see here match that power. Okay, moving on to decimals. Decimals is just another way to talk about fractions involving tenths, hundreds, thousandths, 10,000ths, etc. So when a student first sees an expression 0.2, we have to explain the meaning of such an expression as a fraction, because they've already developed meanings regarding fractions. And when you see 0.2, this is to be interpreted as 2/10ths. Whenever you put a digit right to the right of a decimal, immediately to the right of a decimal, then that's indicating how many tenths we are working with or thinking about. And of course, 2/10ths could be reduced to more simple terms and be written as 1/5. When you have a decimal or a digit that's separated by a 0 away from the decimal, then this 5 is an indication of how many hundredths we should be considering. So this is 5/100ths, which we could reduce to 1/20th. Over here we have, you're going to see the pattern continue. Now we have a non-zero digit, 7, but it's in a position that's 3 positions to the right of the decimal. So this is how many 1,000ths we are working with or thinking about. So you interpret 0.007, and putting this 0 in the front isn't necessary, but I like to put it there to say 0.007. Sometimes you'll see that leading 0 not expressed, which is fine, it's the same thing. Anyway, this stands for 7/1000ths, which does not reduce to more simple terms with 7 as prime. And finally, we have a 6 that's 4 digits to the right of the decimal, so that stands for 6/10,000ths. And these ones, we can certainly divide each of these numerator and denominator by 2 to write this as 3 5,000ths. And this would be simplest terms. But the way you say these things is exactly how you would say, when you see this expression right here, 0.2, or just 0.2, you say it the same way you would say this. You read that as 2/10ths. When you see the 5 in 2 positions to the right of the decimal, then you would say, for the 0.05 is said the same way you would say this, which is 500ths, etc. You say 7,000ths and 6/10,000ths. Notice I'm putting those THs at the end of these numbers to indicate the fraction. Express the number below as a combination of powers of 10. So here we have several different digits in a variety of positions. All of these have different place values, right? The 4 is in the hundreds position, the 3 is in the tens position, the 1 is in the ones position, and then we have a decimal, and then after that we have the 0 in the tenths position, the 9 in the hundredths position, and the 8 in the thousandths position. So when you see a number like this, it's really a combination of powers of 10. So we have 4 10 cubes. We have 4 thousands, and to that we are combining 3 10 squares, 3 hundreds. And to that we are combining 1 10 to the 0. Sorry, 10 to the... Oh, I got these backwards. Scratch those. The 4 is in the hundreds position, so 4 10 squares. The 3 is in the tens position, so 3 10 to the firsts. And the 1 is in the ones position, so you could think of that as 1 10 to the 0. And then the 0 that you see after the decimal is how many tenths we have, which you can express with a negative power. 1/10 is the same thing as 10 to the minus 1. The 9 is in the hundredths position, so we say 9 100ths, and 100ths could be written as 10 to the minus 2. And then finally the 8 is in the thousandths position, which is 10 to the minus 3. And so each of these digits, 431098, because of their positioning relative to that decimal, indicate different powers of 10. So you could also write this, of course, as 4 hundreds plus just 3 tens plus 1 1. Remember, 10 to the 0 is 1. Plus 0 1/10ths plus 9 100ths plus 8 1,000ths. Combine these together and you have this number that's 431.098. For the following decimals, we're going to express each of them as a fraction and then express the fraction in simplest terms. Okay, so when we have 0.12, we have a 1 in the tenths position, so we have 1/10, and we have a 2 in the hundredths position, so plus 2 100ths. Now, if you were to add these together, we use rules for adding fractions, and we would need to get a common denominator of 100. So I'm going to multiply the first fraction by 10 over 10. So multiply the numerator and denominator each by 10. So we could write this first part as 10 100ths, and then add to that 2 100ths. And then now that we have a common denominator, we can just add the two numerators, 10 plus 2, and we have 12 100ths. So this is how you write 0.12 as a fraction. It's 12 100ths. It's 1/10 plus 2 100ths, which winds up being 12 100ths. And then, of course, we can reduce this. Each of these is divisible by 4. By these, I mean the numerator and denominator. So divide 12 by 4, you get 3. And divide 100 by 4, you get 25. So 0.12 as a fraction in reduced terms is 3/25. But the more obvious connection is that when you see 0.12, you think of that as 12 hundredths, which can be rewritten as 3/25. In this next one, we have 0.12. Now, the way to say this one quickly, if you notice the pattern here, we had a 1 in the tenths position and a 2 in the hundredths position. I'm going to read this number, though, as 12 of something, and that 12 of something will be corresponding to the power of 10 that's indicated by the furthest to the right digit here, which is the 2. That's in the hundredths position. So you could view this, instead of thinking of it as 1/10 plus 2 100ths, you could look at this as 12 100ths. We could do something similar here. We have 0.012. We have 0 tenths, 1 hundredths, and 2 thousandths. But I could look at this as the number 12, but 12 what? And that answer will be the 2 is in what position? It's in the thousandths position. So this should turn out to just be 12 thousandths. Let's just confirm that real fast. All right, well, we have 0 tenths, but we have 1 100th. We're adding that to 2 1,000ths. And instead of, I'm not going to bother reducing this to 1 500ths and then get a common denominator. I'm going to keep everything in terms of all the denominators will be powers of 10. I don't want to change that to 500 by that. I don't want to change this to 500. So instead, I'm going to make this fraction here have a denominator of 1,000. So I'm going to multiply the top and bottom by 10. So 1 100th is the same thing as 10 1,000ths. And I'm adding that to 2 1,000ths. And sure enough, now that we have a common denominator, we can see that we have 12 1,000ths. So when you see this decimal right here, you can ignore any leading zeros. Look to that. That looks like a 12, but 12 what? And the answer will be, well, the 2 is in the thousandth position. So you can look at this as being 12 1,000ths. And then now we can think about reducing. Divide each of these numerator and denominator by 3. So this is 4, and then 250th. So we can go even further. We could have divided each by, I meant to divide by 4 each. So 12 divided by 4 is 3. Now we have 3 250ths, and 3 and 250 are relatively prime, so that fraction doesn't reduce to some more simple terms. Okay, now just to get confirmation, I want to type this fraction into a calculator and show you that it turns out to be this decimal. I'm using a calculator called Desmos. It's free, it's online. Just go to desmos.com, and I'm going to type in 3 divided by 250. And notice the decimal it gives me is 0.012, which is the decimal I started with. Also, in this particular calculator, I can click the symbol here on the left and convert my answers back and forth between fractions and decimals. That's in case you do something that isn't reduced, something like 4 divided by 6 has a decimal form. Let me do 4 divided by 8 has a decimal form of 0.5, but in reduced terms, it's 1/2. All right, back to our work. All right, here we have, this is actually a mixed number because it's part whole and part fraction. So we have 1 and, the way to read 1.2 is literally 1 and, so plus 2/10. So we have 1 and 2/10. I'm not going to change this fraction here to 1/5. I want to have my denominators be powers of 10, but I will rewrite 1 right here as 10/10. So this is 10/10 plus 2/10. And now that we have similar size fractions, we can say that we have 12/10. And 12/10 in more simple terms is divide each numerator and denominator by 2, and we get 6/5. And then finally, let's do 1.002. So the 1 to the left of the decimals just stands for 1 whole unit, plus we have 0/10, 0/100, but 2/1000. And again, don't bother writing that as 1/500. Just keep that 2 over 1,000. But do express this 1 in terms of thousandths. So 1 is the same thing as 1,000 thousandths. And so we have 1,000 thousandths, which is equivalent to 1 in value, plus 2 thousandths, which tells us that we have 1,002 thousandths. And now we can worry about reducing this to more simple terms. Divide the top and bottom by 2. The top is divided by 2 is 501, and the bottom divided by 2 is 500. And I do not believe these have any more. I think 501 and 500 are relatively prime, so this is as far as that fraction will reduce to simple terms. Now looking at all 4 of these, you might notice a pattern. To convert a decimal to a fraction, it's really as simple as the following. I view this as 12 something, and the question is 12 what? Well, one way to determine that it's 12 hundredths is to ask yourself how many times would the decimal have to move over to the right so that it's just to the right of the 2. And you can see 2 steps. And so it's possible to write this 0.12 as 12 over 1 with 2 zeros right there, because we did 2 steps to move the decimal, to think of that as 12 instead. This pattern continues, of course. If you look here and you say, okay, I see a 0, 0, and I want to think of that as 12 something. And you'd have to move the decimal 3 times to get it just to the right of the 12. So you want to read this as 12 over a 1 with as many zeros there, 3 zeros. So 12 thousandths. Over here, we just had to move, if I want to view 1.2 as 12 of something, we had to move the decimal over just once to think of that as 12. So put this as 12 over a 1 with 1 0 there. So 1 step there, put 1 0 there. And so 1.2 can be thought of pretty quickly as simply 12 tenths. And similarly here, I see a 1002. I can't really view that as 12 of something, but I can look at that, ignore the decimal, and I want to think of this as 1002 of something. And to move the decimal just to the right of that 2, you have to move it 3 times. And so we put 1002 over a 1 with 3 zeros. In other words, we see 1002 1,000ths. Okay, let's move on. We're going to practice going the other direction now. That is, I give you a fraction, and we're going to turn it into a decimal. Convert the following fractions to decimals. Use equivalent fractions and or long division to get each answer. Then use technology to confirm your answers. Okay, let's first do this approach of what I'm calling using equivalent fractions. If you come back up here and look at some of these problems backwards, for example, look at this fraction right here. If I'd given that fraction and said, hey, convert that to a decimal, then you can think of 12 1/100ths as, you could decompose it so that it's thought of as 1/10 plus 2/100ths, and then from there, just put the 1 and the 2 in the correct positions, so 0.12. Or often there's a shortcut approach. When you have 12 over 100 and you want to think of that in terms of decimals, put it in decimal form, then you start by writing 12 and then you move, so it would be something like this. You write 12 first and then you move the decimal to the left twice because there are 2 zeros there. And so you get 0.12. Those are the gimmicks of expressing or turning a fraction that has a denominator that's a power of 10 into a decimal. So if I were to use that gimmick, then it would be of interest to me to write this fraction 1/2 in such a way that it had a denominator that is a power of 10. So the powers of 10 are 10 to the first is 10, 10 squared is 100, 1,000, etc. So I want to find an equivalent fraction where the denominator is either 10, 100, 1,000, etc. Well, we can turn 2 into 5 through multiplication. So I'm going to begin by multiplying the top and bottom of this fraction, the numerator and denominator, by 5. And that's going to give me 5/10. So once you express 1/2 as 5/10, now that we have a power of 10 down here, it's easy to convert this to a decimal. Well, in decimal notation, that just means do 0.5. That's how to convert 5/10 to decimal. As long as you're working with a fraction where the denominator can easily be multiplied or scaled into a power of 10, then this is a very useful approach for converting fractions into decimals. Another way is to do long division, which is not something I want to emphasize in this lesson, but I will do it quickly. You might recall this process that you've learned before. I'm going to show you this process, although I'm not, like I said, I'm not going to emphasize it in our lecture for this class. So we do 2 divided into 1, but we think of 1 as 10/10. So I put a decimal and I put a 0 after the decimal, and then I say, okay, if I think of 1 as 10/10, and I say, well, 2 divide, or 10/10 split into 2 pieces would be 5/10, or you can just ignore teach you to ignore the decimal and just say, hey, 2 goes into 10 how many times? The answer is 5, but since we keep the position to the right of the decimal, so put a decimal up here in your quotient answer, and then you effectively ignore the decimal, and then you say, okay, well, 5 times 2 is what number? It's 10, and you subtract that from that 10, you get a 0, and when you get a remainder of 0, you stop, and your answer is 0.5. That's the long division approach for getting an answer. And then, of course, using technology to confirm, I would type a fraction in here and say 1 over, or division sign, 1 over 2, and it gives me the 0.5 confirmation. Okay, let's try 3/4. Let's do the equivalent fraction approach. To scale, 4 is not a factor of 10, but it is a factor of 100. So I'm going to scale 4 by 25, and make sure you scale the 3 by the same amount. And this takes us to a fraction that says 75 over 100, so 75 1/100ths, which could be broken down. I'll show you the long way to do this and then the short way. It could be broken down into 70 1/100ths plus 5 1/100ths. And in decimal form, that means we have reduce the first fraction to 7/10 plus 5 1/100ths. And you can see where this is going. 7/10 is 0.7 and 5/100ths is 0.05. So put those together, we have this 0.75. Of course, when you have 75 over 100, you could just start with the 75 and then move the decimal, Right, so the decimal used to be right there, and then just move it to the left twice because we're dividing by 100. So 75 hundredths is the same thing as 0.75. And then let's do this using the long division approach. You would take 4 and divide it into 3. And we're going to put a decimal here and put a corresponding decimal up there and put a 0 next to it. So we're thinking of 3 as 3.0 and asking ourselves 4 goes into 30 tenths. So in other words, 4 goes into 30. Let's just think of that. 4 goes into 30 how many times? It goes 7 times. And 7, we do 7 times 4. Do 7 times 4, not 0.7 times 4. So 7 times 4 gives me 28. Put that here. And think of this as 28 being subtracted from 30. You get 2. Then you don't have a 0 remainder, so you put another 0 there, and that drops down. And we ask 4 goes into 20 how many times? That's really 20 hundredths. That's what we're asking, but we just think 4 goes into 25 times. Multiply 5 times that 4, get another 20, subtract, we get a 0. And we have the algorithm that yields a 0.75. Now there's a lot of, when you do this decimal algorithm for converting fractions into decimal, there is a lot of potential confusion for the students because they're saying, why are you ignoring the decimal? And sometimes you don't ignore it, sometimes you do ignore it, and it can be extremely confusing to the student, this algorithm, and why it produces correct answers. But again, I'm not going to emphasize why the algorithm works in this lesson. We're just going to remind you that there is such an algorithm for converting fractions to decimals. My interest in this lecture was to show you this approach in case you had not seen it before. And then let's go back to Desmos and confirm that 3 divided by 4 is in fact 0.75. So 3/4 is the same thing as 75 hundredths, is how you would interpret this. Okay, 13/5. We have an improper fraction. That doesn't matter. Is it easy to turn 5 into 10 or a power of 10? The answer is yes. If we double 5, we'll get 10. So I'm going to double top and bottom to write this as 26 tenths, which could be broken down into 20 tenths plus 6 tenths. In other words, 2 plus 6 tenths, so 2.6. Or you can just use the idea that you start with 26 with the decimal in the correct position relative to 26, but then when you divide by 10, you move the decimal exactly once to the left because there's 1 0 there in 10. So the decimal winds up being now between the 2 and the 6. So there we go. So 13/5 is the same thing as 2.6. And to do this using the algorithm, we're going to divide 5 into 13. 5 goes into 13 twice. 2 times 5 is 10. Subtract, we get a remainder of 3. So if I want to keep going with decimals, put a decimal here and put a corresponding decimal there. Bring down that free 0 and repeat the question. 5 times what will give me 30? The answer is 6. And 6 times 5 is 30. Subtract that, we get a remainder of 0. And so this is the algorithm approach to determine that 5 or 13/5 is the same thing as 2.6. Let's confirm with Desmos. 13 divided by 5. 13 divided by 5, there we go, is the same thing in decimal form as 2.6. You can also write 13/5 as 2 and 3/5, and 3/5 is 0.6, so you get the 2.6 that way as well by taking a mixed number approach. Okay, this next example, we do not have a way to convert 3 into a power of 10 easily. Like, what would you multiply 3 by, right, to scale it to 10? How about to scale it to 100? How about to scale it to 1,000? Right, not every number is a factor of a power of 10. 3 is one example. So the way to convert this to decimal form, the best way really is just using the algorithm. So we're going to take 3 and divide it into 1. And I'll just do it quickly. Again, I'm not emphasizing why this algorithm works. Put your decimal. 3 goes into 10 3 times. 3 times 3 is 9. Subtract, we get a 1. Bring down a free 0. And we repeat. 3 goes into 10 3 times. 3 times 3 is 9. Subtract it from 10, get a 1, bring down another free 0. We want to keep this up until I get a remainder of 0. But as you can already see that this process is going to continue. It's just not going to end. So these 3's are never going to end. This suggests that 1/3 in decimal form is 0.333, and the 3's go forever. One way to write that, if you recall, is to put a bar over the first 3, and putting a bar over that 3 indicates that 3 should never stop. If you go to Desmos and you type in 1 divided by 3, notice it gives you 0.3, and it gives you a whole bunch of 3's, and Desmos is not showing you all the 3's. It's rounding the number. It's giving you a precise enough number for our practical purposes, but in reality the 3's go forever without stop. Call this a forever repeating pattern in the decimal. Forever repeating, the 3's repeat forever in the decimal notation. 5/7. Let's try this one. Again, 7 is not a factor of a power of 10. 7 cannot divide into 10, 100, 1,000, none of them. It's relatively prime to all powers of 10. And so the only way to do this is the long division algorithm. So we're going to take 7 and divide it into 5. Put a decimal, free 0. Think of that as 50. 7 goes into 50 7 times. 7 times 7 is 49. Subtract. We get a 1. Bring down another free 0. 7 goes into 10 once. 1 times 7 is 7. Subtract. We get a 3. Bring down another free 0. We're trying to get a remainder of 0, then we can say the process is finished. 7 goes into 30 4 times. 4 times 7 is 28. Subtract from 30 gives us a 2. Bring down another free 0. 7 times 2 will get us closest to 20 without going over. 7 times 2 is 14. Subtract that from 20 is 6. Bring down another free 0. And you'll keep this up until either a pattern emerges or until we get a remainder of 0. 7 times 6 is 42. 7 times 7. 7 times 8 is 56. That's what we want in 8. 7 times 8 is 56. Subtract. That gives me a 4. Bring down a free 0. 7 times 5 would be next, is 35. Subtract 5. Bring down a 0. And notice that we're right back at this 50 issue. So the cycle is going to repeat. The next digit is going to be a 7 again. And 7 times 7 is 49. Subtract. And all the work that we've done, all of this is just going to keep repeating. So once you recognize that we're going to repeating, it's a 714285 is going to repeat. Put a bar above that part of it. And let me move my work a little bit so we have some space to fit this on one page. And so in decimal form, 5/7 in decimal form is 0.71428. And then that would just repeat 71428 71428 forever. And the way to establish that is to put the bar above there, 714285. Put a bar above all the part that repeats. And if you want to do approximating, then you can do a wavy equal sign and say, oh, it's close enough. It's about 0.714. And if you want to stop the decimals, you can use an approximate equal sign. Same thing is done often for 1/3. It's approximately 0.33. It's usually what people round it to if they're going to round it at all. The more 3's you put here, though, the more accurate it gets. If I indicate all the 3's, so by putting a bar or doing the dots, then that wavy equal sign becomes an equal sign. If you indicate that all the 3's are there. But if you stop the 3's somewhere, let's say only 2 of them, then you should use a wavy equal sign. Okay, let's confirm 5/7 using Desmos. The calculator over here, Desmos, 5 divided by 7. And there it is, 0.714285, 71428. And notice it has a 6 at the end. That's because it's rounding that last position. It would be a 5 and then a 7, and then they rounded that to a 6 to show you So you're seeing a rounded version of 5/7 here, not an exact. Okay, so this is how you convert fractions to decimal. When you can do this approach that I'm calling the equivalent fraction approach, then I recommend you do that approach. But you always have this long division approach to arrive at your decimal versions of these fractions. Okay, let's move on. Perform the following operations by first converting the decimals to fractions, then using rules for operating with fractions. All right, so addition, 0.5 plus 4.03. So I'm going to convert the 0.5 to a fraction, which is 5/10. I'm going to add that to 4.03, which can be thought of as 403 100ths. And how did I know to make that a 100 down here? Well, I looked up here and I said, okay, well, how many positions to the right would I need to move that decimal so that I thought of this as 403 of something, and it moved twice to make it 403, so I put it over 1,000. Now you could move the decimal 3 spots and put it there, in which case there'd be an extra 0 showing up, and we would have 4,030. But because I moved the decimal 3 positions, then you would put 3 zeros right here, so it'd be over 1,000 instead of 100. But this is going above and beyond. You only need to move the decimal to the end of the last non-zero digit, so twice, in other words. So we don't need that zeros, and we can write this as 403 hundredths. Okay, so once you convert these decimals both into fractions successfully, then get a common denominator. So I'm going to have to multiply the first fraction by numerator and denominator by 10 each, so that's 50 100ths. I'm going to add that to 403 100ths. Now that we have the same size fractions we're working with, we can just add the two numerators. So we get 453 100ths. And then you can convert that back into a decimal form. So 453 100ths, start by writing 453. The decimal would be right there, but when you divide by 100, you're going to move the decimal left twice. And we have 4.53. Now, some algorithms for doing this, which I'm just going to mention briefly but not emphasize, is to align the two numbers with the decimals aligned, and then put zeros wherever you need them, whatever, and then just add by column and carry your ones as you're expected to do. So 4.53 is the algorithm approach. I'm not going to emphasize the algorithm approach. I want you to think of these decimals in terms of fractions, and then use your rules for adding fractions. 0.62 minus 0.15. So 0.62 is the same thing as 62 100ths. And we're going to subtract from that 15 100ths. Well, these already have a common denominator, so we can just subtract 15 from 62, which gives me 47. So we have 47 100ths, which in decimal form is 0.47. Multiplication, 3.1 times 10. Well, there's lots of ways to think about this. 3.1 is 3 1/10. So you could think of this as a mixed number. It's 3 1/10. And we're going to multiply that by 10. Now, if you were to invoke commutative property and think of 10 as the multiplier, then you would be saying, I want 10 3s and 10 1/10. Or you could leave the 3.1 as the multiplier and say, okay, we want 3 10s and 1/10 of 10. Either way you think of this, numerically, you're going to get the same result. You're going to get 3 10s, which is 30, and we're going to add to that 10 1/10, which is 10 tenths. Right, all I did is use the distributive property. Right? I did 3 10s, which is 30, and 1/10 of 10, which is 10 tenths. And so we get 30 plus 1, which is 31. If I do 3.1 times 1,000, and it doesn't matter if you think of the 1,000 as the multiplier or the multiplicand, you'll get the same result. So you could put the 1,000 in the front if you want to insist that you think of 1,000 as multiplier and insist that you put multiplier in front. let's go ahead and just do it that way just to show you it doesn't matter. You can think of the 3.1 as, again, 3 1/10, and say, okay, I want 1,000 threes. Well, that's going to be 3,000, and 1,000 1/10. Well, 1,000 1/10, 10 1/10 makes 1, and 1,000 is 100 tens. So if 10 1/10 makes 1, then we have 100 of those, and we have 100. 1,000 1/10 will wind up being just 100. And when you combine 3,000 and 100, we get 3,100. All right, so there is, of course, shortcut thinking for when you multiply decimals by powers of 10. If you were to multiply by any decimal by 10, the net effect really is just the fact that the decimal goes to the right 1 unit. So 3.1 became 31. And I knew to go to the right 1 because there's exactly 1 0 here. Or you can think of, if this had a power on it, that power would be a 1, and that would also indicate how many times you go to the right with your decimal. Over here, something similar, right? 1,000 is the same thing as 10 cubed, right? There's 3 zeros here, or your power would be 3. And so this tells us to take this decimal and go 1, 2, 3 steps to the right, and that's what creates, right? 1, 2, 3, that's what creates this 3,100. So multiplying by powers of 10 winds up being really that straightforward. Moving the decimal to the right an appropriate number of times. Now when you divide by powers of 10, right, to divide by 10 means to, and using the algorithms for division, dividing by 10 means you're going to multiply instead by 1/10, right? You do the invert and multiply algorithm. And that's a true, we justified that was the case for both partitive and quotative meanings for division, but now we're putting those meanings aside and just doing the rules for operating with fractions. So dividing by 10 means to multiply by 1/10. And so now we're going to do 1/10 of 3.1, or you can think of this as 3.1 copies of 1/10. So whether you think of the 1/10 as the multiplier or the multiplicand, it won't matter. The end result will be you do 1/10 of 3, which is 3/10, and then 1/10 of 1/10, which is, let's go ahead and write this out instead of just saying it. So 3.1 is the same thing as 3 and 1/10. And we're going to multiply that by a 1/10. Using the distributive property, we're going to do 1/10 of 3, or 3 1/10. Let's think of the 3 as the multiplier, so we're going to do 3 1/10. So no, that's the same thing as 3/10. So we get 3/10, and then we do 1/10 of 1/10. And 1/10 of 1/10 is 1/100th. And you put this in decimal form, that just means, well, 3/10 is 0.3, and we'll add 1/100th to that, so we'll put a 1 next to the 3, and we get the 0.31. So when you are dividing, or let's do this next one, and then I'll generalize. 3.1 divided by 1,000. So again, we have 3.1, which is 3 1/10. And instead of dividing by 1,000, we're going to multiply by 1/1000th. So invert and multiply. And then use the distributive property. So we have 3 copies of 1,000th. That's 3,000ths. And then we have to do 1/10 of 1,000th. That's going to be 1/10,000th. You just multiply the two denominators. 10 times 1,000 is 10,000. Using our rules for multiplying fractions. And 3,000ths is 0.003. That's 3,000ths. And add to that 1/10,000ths. Just put a 1 next to the 3 there. And so we have 0.0031. Okay, so now let's look at the shortcuts for when you're dividing by powers of 10. So when you divide by 10 to the first, you just take that decimal and you move it left 1. So it becomes 0.31. Here we divided by 1,000, which is the same thing as 10 cubed. That tells me to move the decimal left 3 times. So that puts a 0 here, a 0 here, and then the dot will eventually move there, so we get 0.0031. So in summary, looking at when you multiply by powers of 10, you move the decimals to the right. In both cases here, in this case here, you multiply to the right 1 position, and here you move the decimal to the right 3 positions. But when you divide by powers of 10 or multiply by their reciprocals of powers of 10, keep in mind, let me squeeze this in here, that to multiply by 1/10 is the same thing as to say to multiply by 10 to the minus 1, right? To bring in this discussion of negative powers that we talked about a second ago. So when you multiply by 10 to the minus 1, you go left 1 with a decimal. Okay. Same thing can be said here. We had 3.1 essentially times 10 to the minus 3. So this says take 3.1 and move the decimal left 3 spots. And we get 0.0031. Only 2 zeros there, okay? Okay, let's continue operating with decimals. I'm going to work with now multiplying 2 different decimals together. 0.5 times 0.24. I'm going to first convert both of these to fractions and then just operate with the fractions, and I'll convert my answer back to decimal form. This is a pretty good consistent way for doing these kinds of problems. There are little tricks you might have learned where you just you put the 0.5 and you multiply it to the 0.24. You've seen this before. You ignore these decimals, you get an answer, and the answer is going to be 120, and then you say, okay, there's a total of 1, 2, 3 decimal spots. You move the 3 over and you get 0.12. I'm not going to emphasize this. I'm saying that fast. I'm not going to emphasize that procedure. I want you to think of these in terms of fractions. So we have 5/10, which is what 0.5 is. We're going to multiply that, put a dot. Well, I'll put the x. The dot starts to look like a decimal, so we'll use the x for multiplication. And 0.24 is 24 100ths. Now don't worry about simplifying these just yet. In fact, don't worry about simplifying them at all right now. I'll do this 2 ways. If you leave these denominators 10 and 100, and when you multiply, you don't need common denominators. You just multiply the numerators. So we do 5 times 24, which is 120. And then we do 10 times 100, which is 1,000. So the end result is 120 thousandths, which is the same thing as doing 120 divided by 1,000, which means that we move the decimal. We start with 120 with a decimal right there, and we move it left 3 spots because we're dividing by 1,000. So the end result is the 0.12. This 0 here, you don't need to write. You don't need to have final zeros at the following a decimal. Leading up to a decimal, yes. Like if I say 25 and 250, crossing off that 0 changes 250 to 25, which is not the same value. But after a decimal, if you have a extra 0, you don't need to write that extra 0. Now let's confirm our answer using technology, where we did 0.5 times 0.24. There we go. And the answer is 0.12. Now you could have taken this a slightly different route and simplify the fractions before you multiplied. So let me just show you that real fast. So again, write this instead of 5/10, simplify that to 1/2. And instead of 24 hundredths, simplify that to, let's say I can divide by 4, so that gives me 6/25. Oops, and this is times, not plus. This takes me to an answer that's 6/50. And you say, okay, well now I have the trouble of converting 6/50 to a decimal. Let's use the equivalent fraction approach, right? 50 is a factor of 100, so it's easy to scale that up to 100. So I'm going to double the 50 and double the 6. I'm not going to do any long division here. So that gives me 12 over 100, 12 hundredths. And 12 hundredths is the same thing as 0.12. I'm going to put the lead 0 there on that decimal as well. And so you wind up getting the same result. You choose your approach. I kind of like just keeping those denominators as powers of 10 and that's going to guarantee your new denominator will be a power of 10, and that's easy to convert back into a decimal. So there's a good case for just going with this first approach. In other words, not simplifying these fractions before you multiply. Let me make that an x again to be consistent. Okay, so 1.2 times 5.04. So 1.2 is the same thing as 12 tenths. We're going to multiply that with 5.04 is the same thing as 504 hundredths. So now we just have to multiply 12 and 504. So that's going to take a little bit of work here. I'm going to do that work over here on the side, or we can just use a calculator. But if we're doing all this by hand, you'd have to reduce these fractions anyhow. Let's do 12 times 504. That's going to be, I'm going to break up 12 into 10 plus 2. So I'm going to do 12 copies of 504. I'm going to do 10 copies of 504 plus 2 more copies of 504. So we have 5,040 plus 1,008. And put these together and we get 6,048. So 12 times 504 is the same thing as 6,048. And then now multiply the denominators. 10 times 100 is 1,000. And to convert this back to decimal is very easy because our denominator is a power of 10. So it's like dividing by 1,000. So I'm going to move the decimal left 3 spots. So 6.048 is the result. Let's confirm that. 1.2 times 5.04. 6.048 is the result. And let's do some division. I'm going to show you multiple ways to do the division. One is to do, like we did before, convert these decimals to fractions and then use your rules for working with fractions. Let's do that way first on this one here. So we have 24 hundredths, which is what 0.24 is, and we're going to divide that by 3 tenths. When you divide by a fraction, you instead multiply by the reciprocal. So we're going to multiply, let me use an x there instead of a dot, multiply by 10 thirds, and then you simply multiply across, and then try to simplify the result. So 24 times 10 is 240, and 100 times 3 is 300. And then ask yourself, okay, 10, I could divide each of these by 10 to begin with. So I'll get rid of the extra zeros and rewrite this instead as 24 thirtieths. Then I see that 3 divides into 24 and into 30. So 3 goes into 24 8 times, and 3 goes into 30 10 times. And I say, oh, I could have gone even further. Divide top and bottom by 6. 24 divided by 6 is 4, and 30 divided by 6 is 5, so we get 4/5 in the end. Now, 4/5 is what decimal? Well, in order to convert this to a decimal, let's get 5 back up to a power of 10, so I'm going to double the 5 and double the 4, and that gives me 8 tenths, which in decimal form is 0.8. There are also a lot of different algorithmic approaches for doing this. I'm not going to emphasize those here. I want you to think of this in terms of fractions and simplifying fractions and converting the fractions back into decimals. So we have 0.8. Let's go ahead and confirm. If I take 0.24 and I divide it by 0.3, we do get 0.8 as a result. Okay, and I'll read this next sentence right here. If possible, also calculate the result by expressing the quotient as a fraction and then strategically rewriting the fraction in an equivalent form. Now, what do I mean by that? So the alternate approach is to take this statement right here and write it, instead of saying division, write this as straight up fraction, which is, in other words, say it's 0.24 over 0.3. And now I'm going to convert this to an equivalent fraction by scaling the top and bottom by a power of 10 so that there are no more partial numbers. So they're all whole numbers. In other words, ask yourself, looking at the numerator and denominator, how many times you need to move the decimal over the numerator to make this a whole number, to get it to the right of the 4. In other words, make this 24. And that's twice. Well, how many times do you have to do it to the 0.3? Well, just once. What's the largest of these two? Well, they're going twice. So I'm going to scale the top and bottom of this fraction by 100. and watch what happens. Well, to multiply 0.24 by 100 is straightforward. Just move the decimal to the right twice and makes it 24. Now multiply 0.3 by 100. You also move the decimal twice, so that turns 0.3 into 30. And now we're at the point essentially right here again, all over again. So this will wind up becoming 4/5. Let's just do this. ... We've already repeated this work, so 0.8 will be the result this way. All right, for this next example, I'm only going to do this approach. Okay, so we have 0.25 divided by 0.03. So I'm going to write that as 0.25 divided by, or as a fraction, 0.03. Now I'm going to scale both of these by the smallest power of 10. That would turn both of these into whole numbers, which again is going to be 100 in this case. So I'm going to multiply the top by 10 squared, or 100, and multiply the bottom by 100. That'll guarantee both of them become whole numbers. So that leads me 0.25 times 100 is 25, and 0.03 times 100 is 3. So we get down to 25/3. Now I want to convert this back into a decimal. And I can't use the equivalent fraction approach like I did here. When I had 4/5, it was easy to scale 5 into a power of 10, just double it. But to scale, or 3 is going to be relatively prime to all powers of 10. It doesn't divide into 10, 100, 1,000, etc. So the best way to do this one will be our long division approach. So we'll take 3 and divide it into 25. 3 goes into 25 8 times. So we do 8 times 3 is 24. Subtract. We get a 1 here. Put a decimal in a decimal. Free 0. Bring that free 0 down and repeat. 3 times what will go into 10 without exceeding it? Well, 3 times 3 makes 9. Subtract. We get a 1. So this is going to repeat. All these free zeros we bring, we're just going to keep this process up. So we're going to keep getting 3s. So to convert this one into decimal, it's equal to 8.3 with the 3 repeating. Or if you wanted to round it, you could say approximately 8.33. Okay, let's confirm this one. We're doing 0.25 divided by 0.03. 0.25 divided by 0.03. And notice we get 8.3 and a bunch of 3s. Now this, of course, is not showing you all the 3s because there's infinitely many. If you convert that to a fraction, notice it just writes that instead as 25/3. Right, which is what we had here by using this approach. Okay, let's keep moving on. Number 6, percentages. The word percent means to divide by 100. So when you see this word, the per means divide and the cent means 100. So it literally means just divide by 100. And the symbol for a percent, as you all are familiar with, is this symbol here. It looks like a fraction with a those are not 0 and 0 with being divided. It's like saying that you have a blank space and a blank space. So notice it has this as fraction form, which they've turned into this symbol here, which means percent. But it has a very specific meaning now, though. It means per 100. So when you see 22 with this symbol right here, of course you do say this 22%, and it really means you do 22 divided by 100. So you would say, okay, percent means divide by 100. That's how you convert this symbol into a math statement. Divide by 100. And write that in fraction form would just look like 22 hundredths. And then can we simplify this at all? This will become 11/50ths in most simple terms. Now in decimal, the best way to get the decimal form is to launch from this hundredths term, 22 hundredths. So we have 22 hundredths, which means we start with 22 and move the decimal left twice, so 0.22. So 22% is the same value as 0.22. Now if I start with a fraction, and I want to convert it to a percent and to a decimal, the best way to do this is to get a 100, to scale the 5 so that it's 100. So in other words, I'm going to scale this by 20 and 20. Scale the 4 and the 5 each by 20. So you can get that 100 down in the denominator. So it's 80 hundredths. So now you just ignore that hundredth and just say that's the same thing as 80%. right? Because this symbol means divide by 100. So 80% is the same thing as 80 hundredths. And then in decimal form, 80 hundredths is 0.80. If you start with the decimal form, notice we have 1.3. You can think of that as 1 3/10. We want to express this in terms of hundredths. So I'm going to do that. I'm going to convert it to fraction form by starting with the 1.3. Writing this as 13/10. And then keep scaling so that I get it per 100. Right, percent is always per 100. That's the denominator you want when you're working with a percent, is 100. So I'm going to scale by 10 and 10. And this winds up being 130 hundredths. Right, if you take 130 hundredths and move the decimal left twice, right, if you do 130 and move the decimal left twice, you get this 1.3. Right, so 1.3 is 13/10, but that's the same thing as 130 hundredths. So that tells me what the percentage is. It's this numerator. 130% is the same value as 1.3. So when you convert decimals that are more than 1 into percents, like 1.3, your answer is going to be more than 100%. But decimals that are less than 1, like 0.8 and 0.22, or give you percents that are less than 100%. We could put an extra column in here or an extra row, where I say, hey, what's 100% in fraction form? Well, it's just 1 over 1. It's just 1. In decimal form, it's 0.01. Oh, I take that back. In fraction form, 100% is 1. In decimal form, it's also just 1. There's no real difference there in fraction form and decimal form when you're working with just 1. Where if I did 1%, this literally means 1/100th, 1%, and that means in decimal form is 0.01. Right, just extra rows there to think about. Okay, to find a percentage of something implies a multiplicative calculation. Consider the statement below. Express it as a multiplicative statement and then justify the claim. So when you say something like 22% of $500 is $110, what this means multiplicatively is that 22% times $500 is equal to $110. So this English sentence here is communicating a multiplicative relationship as indicated by this operation. Now we're going to confirm this. Well, 22%, just convert that to a decimal or decimal or a fraction. Let's go fraction route. So it's 22 hundredths. We're going to multiply that by 500. Then we multiply the numerator 22 with the 500. And 22 times 500 is, make sure I get this right, it's 11,100. Because we do 20 500s, that's 10,000. 2 500s is 1,000, so 20 500s is 10,000, and then 2 more 500s. Yeah, so 11,000 is what you get when you multiply 22 and 500, but that's hundredths. And so we take 11,000 and move the decimal. Let me get rid of that comma. And then move the decimal to the, start with 11,000 and move the decimal left 2 spots. Right, so here's 11,000, but move the decimal left 2 spots. So in other words, I don't need to write those zeros, and we have just 110. When you do a percentage that's less than 100% of something, then it reduces that amount. So 22% is like doing a fraction, a proper fraction of 500. That's why we have a number that's less. But if this had been a percentage more than 100%, then we'd get an answer here more than 500. Okay, now percentage applications are either missing multiplier, which means a missing percentage. Notice that our structure here, the role of the multiplier is the percent, and then these have similar units. You can think of the percentage as a unitless multiplier, a scale factor. So that means the multiplicand and the product will have the same unit, because this number here is unitless. That's one way to think about multiplication. So either there's 3 components in a multiplicative statement, right? Multiplier, multiplicand, or product. given any two bits of this information, you should be able to find the third. And that's hence your three different percentage tasks, generally, that we have. So solve each task. What percent of 5 is 3? When you see what percent, you're saying, okay, well, what percent means we don't know the multiplier. So something you do is you can put like an A for the multiplier. Of 5 is 3. So what percent becomes an unknown thing. Of 5 is times 5 is 3 is equal to 3. So we're effectively trying to figure out what A is. So we're doing A times 5 is 3. So A can be found by doing, to find a missing multiplier, we're doing quotative division. Right, so we're saying, okay, well, do 3 divided by 5, essentially. Or in other words, 3/5. That's what A is. We'll convert 3/5 to a decimal by multiplying, or get it to a fraction where we have a 100 down there. So we multiply by 20 and 20. So we have 60 hundredths. And then that's easy to convert to a percent by just the per 100 just is replaced by the symbol. So 60%. So when the question is what percent of 5 is 3, the answer is 60%. If you do 60% of 5, you'll get 3. 20% is of 8 is what? So now we know the percent, we know the multiplier. 20% is of 8, so times 8 is what? This is what we don't know. I'll use A to represent what we don't know. So here we just have to, this is a missing product task. We just have to multiply 20% and 8. 20% in fraction form is 20 hundredths. We're going to multiply that by 8. And this is what A is going to be. So let me write like this. A is equal to, and then keep this work going. 20 hundredths times 8. Let's multiply the 8 and the 20. I'm not going to bother simplifying this fraction because I want to leave the per 100 down there. Well, actually, that's not true. I don't care about leaving the per 100 down there. You could simplify the fraction up front, or you can simplify it later. Let's go ahead and leave that as 20 hundredths and multiply by 8. So we just do 20 times 8 is 160, and that's hundredths. And then we start reducing this to more simple terms. 160, it's true that you could say that this is 160% as an answer, but we're not looking for a percentage. We're looking for a product, which is going to have the same unit as whatever 8 had. So we don't want to frame our answer in terms of percent. So don't go this route. Instead, boil this down to a simple, more simple number. Divide each by 10 is 16 tenths. Divide each by 2 next is 8 fifths. And 8 fifths you could write as a mixed number as 1 and 3/5, which you could write this back as 1.6. You know, there's so many different ways you can write an answer here, but in the end, I would say any of these three are all good answers. So 20% of 8, let's say 8 was measured in dollars, just to give something to think about. 20% of $8 would wind up being 8/5 dollars, or 1 3/5 dollars, or $1.6, or in other words, $1.60, if money was the context. And then finally, 15% of what is 21? So we know the percentage. 15% of what, we don't know, we'll put the A there, is 21. We're trying to figure out what the initial amount is, if you will, and not the resulting amount. We're trying to figure out the multiplicand. So A can be found by doing a partitive division task. And it's going to be, let me first write this in terms of, no, let me do the division. A is equal to the product of 21 divided by 15%. And this is a partitive interpretation. We're trying to find a missing multiplicand. And 15%, we want to convert that to a fraction. So we're really doing 21. Instead of putting it over, let me use the division symbol. We're dividing by 15% to get A. And we're going to interpret 15% as 15 100ths. This time I am going to go ahead and simplify that 15 100ths. We're going to do 21 divided by, divide 15 by 3, by 5 is 3, divide 100 by 5 is 20. So we're doing 21 divided by 3/20ths. And invert and multiply would come next. so times 20 thirds. And now we just have to multiply 21 and 20. It's going to be 420 thirds. So there we go, 15%. Oh, and 420 is divisible by 3, so we can keep going. 420 divided by 3 is 140. So there we go. This one actually became a whole number. So 15% of 140 will be 21. This would be rather easy to verify. You would just show that 15% times 140 will give you 21 as a way to verify this answer. Okay, now let's move on to discussing rational, irrational, and real numbers. The rational numbers are all fractions formed by dividing two integers. Now remember what the integers are. It's important that you know these terms. When I say integers, I'm talking about all the counting numbers. 0 is in there as well. So remember, the 1 through infinity, 1 and up, the counting numbers are natural numbers. Includes 0 is the whole numbers. And the integers also includes all the negative counting numbers. So this is the set of integers, all whole numbers and their negatives. Gives you the integers. If you divide any two integers, you have what's called a rational number. If you recall, the set of integers was the bold Z. If you look back in our notes from earlier, then the integers is the bold Z, stands for all the whole numbers and their negatives. The rational numbers are fractions formed by dividing two integers. Use set builder notation to describe the set and then give several examples. Okay, well, the symbol for rational numbers is a bold Q. Sometimes you'll just see the Q be bold like this, but if you don't want to scribble, essentially, you can put a little bar right there, and this is considered a bold Q when written by hand. Same thing was true for this bold Z, right? Normally in print it's just a bold Z, but when you don't want to scribble, you can just put an extra bar right there and call that a bold Z. So set builder notation is a set of all fractions, so we're going to say A over B, such that A and B are integers. So here's a good way to describe the rational numbers. All fractions where the numerator and denominator are an integer. You can also say, use more math notation to represent this. And say, in the set of integers. Right, these mean the same thing. Now I'll give several examples. Okay. Take any integer, remember it could be positive or negative, and divide it by another integer. So this is really up to you to make up a whole bunch of answers here. We could have, for example, 10 divided by negative 2. So there's a fraction of two integers. And that winds up being just negative 5. With a partitive or quotative interpretation, if you recall, 10 divided by negative 2 is negative 5. You could do, your answer doesn't have to simplify to a nice whole number. Like you could do 7/14. 7 and 14 are both integers, so when you create a fraction out of them, this is the same thing as just 1/2, but so 1/2 is a rational number, so is negative 5. You can involve two negative numbers, something like negative 8 over negative 6. If you recall, a negative divided by a negative is a positive. We discussed that back when we talked about integers and their operations. So this would be a positive, and you can also reduce these 8 and 6 to 4/3. When you take a rational number and you reduce it to simplest terms, then you'll see that every rational number has multiple ways of being expressed, right? For example, you could say 3 is the same thing as 6/2. You can say it's the same thing as 9/3. You can say it's the same thing as negative 15 negative-fifths. Right, all of these, there's infinitely many ways to express the same single number. But if you take any two integers and divide them, you create what's called a rational number. The only one stipulation is that b can't be 0. So this is probably something we should mention up here in our set builder notation, because to divide by 0 is not possible. So we should specify that b can't be 0. And why can't you divide by 0? Like, what does it mean if you have 6, 0 with a partitive and quotative meaning? This is just a nonsense statement, because you would either be saying how many zeros make 6, and the answer is you can't. It's not possible to combine zeros to make 6. And the partitive question would be 0 whats make 6. 0 copies of what will make 6. Well, to do 0 copies of something, just zeros out. So you can't do 0 copies of a number and get 6. So either way you think of this, partitive or quotatively, it's not possible. But you can't have 0 in the numerator. So you could say, hey, you have 0 and you divide it between 2 kids and each kid gets 0. Or how many 2's make 0? And the answer is 0 2's will make 0. So this is okay. So 0 is a rational number. Or it's a rational number, because you can think of it as 0 divided by 2. For that matter, you can think of it as 0 divided by anything that's non-zero, 0 fifths or 0 negative thirds. And all of these things will simplify to 0. Okay, regarding negative rational numbers, if you have negative 60 divided by 3, if you think of this in a quotative sense, it's how many 3's need to be copied or how many 3's need to be combined or removed to make negative 6. And the answer is you would want to remove 2 3's to make negative 6. Now, I'll leave the imagery off, but if you remove 2 3's, you will form negative 6. So the answer to this is negative 2. That's a quotative meaning. The partitive meaning is 3 whats make negative 6. 3 copies of what number will make negative 6, and that's the answer to that is also negative 2. Right? Whether you're thinking partitively or quotatively, the numerical answer to negative 6 divided by 3 is negative 2. What about 6 divided by negative 3? The partitive meaning is remove 3 copies of what to make 6? Well, you need to remove negatives, copies of negatives to make a positive. So if you remove 3 copies of negative 2, you'll get 6. The quotative meaning is how many copies of negative 3 need to be removed or combined to make 6, and the answer is remove 2 copies of negative 3 to make negative 6. So either way you think of this, quotatively or partitively, you have negative 2 as a numerical result. And then over here, when you put the negative perfectly in front of the fraction, the order of operations says consider the number first and then do the opposite of it. So here this is 6 divided by 3, which is going to be 2, whether it's partitive or quotative. And so you do 6 divided, so you get negative 2 still. But you do 6 divided by 3 first, and then you do the negative last. Now notice in each case, numerically we get negative 2. Even though the partitive and quotative ways of thinking are very different, you get the same numerical answer. So when we're thinking just more superficially and as far as numbers are concerned, you're seeing here that where you put the negative when you have a fraction of 2 numbers, where one of them is negative and the other is not, it doesn't really matter. So if you have a negative a over a b, you can say that's the same thing as a over a negative b. It doesn't matter where you put that negative sign. And sometimes people just like to put it right directly in front of the fraction, like negative a over b. So you have some freedom when you're working with a negative fraction, right, to put the negative sign in a variety of places. Now we're going to perform some operations. All the rules that we learned about operating with fractions and or the rules for operating with integers, like when to keep the sign, when to change the sign, things like that, all apply to when you're working with rational numbers, so fractions and or negative fractions. So you have 5 thirds plus 7 negative thirds. Well, when you have a fraction here that's a negative fraction there with the negatives down associated with the denominator, I like to just move it up and associate it with the entire fraction. So I think of this one instead as 5 thirds plus a negative 7 thirds. And if you recall, when you add a negative, it's the same thing as just subtracting. So this really can be thought of as 5 thirds minus 7 thirds. And now we can use the rule for combining fractions. We have the same denominators, we just have to combine the numerators. And we're thinking in the world of integers, so doing 5 minus 7 is okay. We get negative 2. So we have negative 2 thirds, which, again, this negative here could be now moved. Right? You can move that. You can leave it right where it's at, which is fine. You can move it to the middle, or you can move it to the 3. You can put that negative anywhere, really. Let's just leave it there, though. Here we have something similar. We're subtracting, but a negative fraction is present here, 3 over negative 2. So I prefer to think of this as doing 5 thirds minus a negative 3 halves. But when you remove a negative, when you remove debts, you get assets, right? If you think of money. So our rule for subtracting a negative is to add instead. So we really just have to add 5/3 and 3 halves. And now we need a common denominator. We need to write these in terms of sixths. So this is 10 sixths plus 9 sixths. And so we get a final answer of 19 sixths. And that is as reduced as it gets. When you're multiplying a positive times a negative, when we talked about integers, the result was a negative. Well, it's also true when you're working with rational numbers. So we know the answer will be negative. You could also just move this minus sign and associate it with the top number if you want. In other words, you could do something like this. 5/3 times negative 7 halves. And associate the negative with the numerator. And then you just use your rule for multiplication of fractions, multiply the numerators and multiply the denominators. So we get 5 copies of negative 7, that's going to be negative 35. And then 3 copies of 2 is 6. So we get negative 35 sixths. And that does not reduce at all. You could have done the opposite in that you could have associated the negative with the 2 down there, in which case your answer would have the negative down here. But again, that doesn't really change your answer. You can put the negative in the front if you want, or you can leave it up either with the numerator or denominator. You have some freedom there. And now we're going to do negative 5/3 divided by 10 over negative 7. I'm just going to leave the negatives where they are currently, but I will use the invert and multiply instead of divide by a fraction. So we have negative 5 over 3 times a negative 7 over a 10. So we just invert this fraction and multiply instead. And now I just multiply the numerators. Remove 5 copies of negative 7 will give you a positive result, 35 in fact. And then 3 copies of 10 gives me 30. Right, so I'm just using the rules we had for multiplying integers next. Negative 5 times negative 7 is positive 35, and 3 times 10 is 30. And then this fraction, though, is not in reduced terms. We could go further. 35 is divisible by 5, so it's 30. So this is 7/6. And there's our answer in most simple terms. Okay, last slide here. The real numbers are all possible numbers corresponding to a position on the continuous real number line. So I've drawn a bold number line here with little arrows that point left and right, suggesting it goes forever both directions. Somewhere in here there's going to be a position we call 0, and then you go over 1 unit, over 2 units, etc. Try to make these evenly spaced. And there, so far, we see all the whole numbers. If I throw the negatives on here as well, we get all the integers. So I'm seeing all the integers present. But there are numbers in between, right? Because this number line is continuous. Like, what if I pick a point right there and say, how far is that from 0? What's that number, the value of that position? How far to the right of 0 are we? Remember, positive numbers indicate that you are to the right of 0, and negative numbers indicate a distance that you are to the left of 0. And if you were to zoom in really close to here and say, okay, well, let me break this piece here into fourths. Right, so you would say there's 1/4, here's 2/4, which is a half, and here's 3/4. Right, so you could throw some rational numbers in there too and place them on the number line. But even between them, there are, the more you can keep zooming in, and there's still more and more points. There is no gaps between the possibilities. This is a continuous number line, right? There's a point on here that, let me see if I can grab it, and only it, that no matter where you put it, it's going to be a certain distance either to the right of 0 or a certain distance to the left of 0, and you're free to move it in a continuous way to any distance. Well, all of these little positions represent a different number, and they're called real numbers. So you have all these different distances to the right of 0 and all these different distances to the left of 0. And all of those are called the set of all real numbers. Well, it turns out that the integers combined with all the rational numbers do not form all possible points on this continuous number line. That there are other points that are not considered rational numbers. Other locations that do not correlate with rational numbers. They correlate with numbers that we call irrational numbers. Now, by just the term irrational means not rational. So the irrational numbers are all real numbers that are not rational. In other words, irrational numbers cannot be expressed as a fraction of integers, because rational numbers can be. Irrational numbers have decimal expressions that do not terminate, nor do they settle into a forever repeating sequence of digits. Now, where did we see that before? It was up here when we converted fractions to decimals. Let me back up a little bit. In some cases, like these top three cases, when I did long division, eventually I was able to get a remainder of 0, which means my expression for the decimal expression, we say, was a terminating decimal. So 0.5, and then we stopped. 0.75, and then stopped at that 5. 2.6, and then stopped. But these other two cases, we say these were non-terminating decimals. So 0.3 repeated forever and did not terminate. It did not become just zeros forever. So the 3's kept going, and the part that repeated was just the 3. In the case of 5/7, again, we had a non-terminating decimal. We had a forever repeating sequence of digits, and that was the 714285. That repeated forever. And so with rational numbers, whenever you do a fraction of two integers and you divide them, one of two things will be true. You're going to get a terminating decimal, like you got in these three cases, or you're going to get a non-terminating decimal, like you got in these two cases, but the non-terminating decimal will have a repeating sequence of digits somewhere involved. Irrational numbers, when you put them in decimal form, do not have repeating patterns. Now, I'm not going to jump into the irrational numbers in too much detail, but some of them you've seen before. The classic examples are like radical 2, square root. This means the square root of 2. And if you go for a calculator and say, hey, what's the square root of 2? It's going to give you a decimal form. Now, this is showing you a terminating decimal, but it's rounding your answer. There's actually more digits the digits keep going forever. And as you can clearly see from what we see currently, there is no repeating sequence of digits. It does not settle into a pattern. And I don't have this square root of 2 thing memorized. 1.414213. I think I got that right. And then there's digits forever, but no pattern, no repeating pattern. For approximating purposes, often people will just cut off some of the digits and say, oh, this is about 1.4, and call that approximate. But square root of 2, in its exact form, you would not be able to write it exactly in decimal form, because it goes forever and there's no pattern to establish. You can't put a little bar above something and say, that repeats forever. It just doesn't happen. So really just writing square root of 2 is the best way to write this in an exact way. Pretty much any radical that doesn't simplify, like radical 3, is going to be an irrational number. Another famous one, of course, is pi, which is 3.14159, and then there's digits go forever. Again, no repeating pattern for pi, so that's also, let me just copy that. No repeating pattern for pi, and for practical purposes, most people will round pi, say it's about 3.14. So there's all these different possible numbers that are on the number line. Like square root of 2 would be on this number line. Square root of 2 would be, it's about 1.4, so it's in this area right here. Pi is about 3.14, so it's about there. Negative pi would also be an irrational number. If you took square root of 2 and removed 1, you get about 0.4, so there's square root of 2 and you remove 1, that's also an irrational number. But they do occupy positions on the continuous number line, but there's no way to write them as fractions of integers. So they're called irrational numbers. Contrary to irrational numbers, rational numbers have decimal forms that terminate or have a forever repeating sequence of digits, as we discussed. And we're going to demonstrate that each decimal below is in fact a rational number. Let's start with a terminating decimal, 1.042. Well, this is extremely easy to convert to a fraction of integers. Just move the decimal over 3 times to make it 1024 and divide it by an appropriate power of 10. This is converting a terminating decimal to a fraction of integers is as easy as this. Now, whether or not this reduces to more simple terms is a different question, but clearly you can see that 1024, which is an integer, divided by 1,000 is also an integer, and that makes this decimal. All terminating decimals can be written as fractions of integers. What do you do if you have an example of a non-terminating, but there is a clear pattern? Like notice the 0.24 keeps repeating. So I could put a bar just above the 1.24, or put above the 0.24, and just shorten this and say this instead. Right, that's the same thing. The 2,4 repeats. Well, I'm going to show you one way to turn such a thing into, figure out what fraction it is. I'm going to call this number a. And then I'm going to ask myself, how many times would I need to move the decimal over so that it is at the start of the next cycle? So I need to move it over twice. So I'm going to, how do I move the decimal to the right twice? Well, you multiply by 100. So 100 times a is going to be negative 124.2424, etc. So the decimal just got moved over twice. And now I can also effectively ignore this minus sign, and just consider doing the positive version. So let me write that more formally. Let's not call the negative number a. Let's just do the a is the positive version of this. So a is positive 1.2424, etc. 100 times a is 124.24, etc. And what's convenient here is that the decimal parts here are now identical. Right? The 0.24 repeating forever you see in both spots. So when I subtract these two values, if I'd say, okay, let me also rearrange this, put this down here, and then do some subtraction. You have 100a minus 1a, that's going to give you 99 a's. And then when I do 124.24 repeating minus 1.24 repeating, right, the 0.24 repeatings are going to cancel, and I just have to do 124 minus 1, which is 123. And then I can just divide by 99 to get a. So we know that this so the negative of this would be this negative decimal that we see here. So that tells me that negative 123/99 is the same thing as negative 1.24 repeating. Let's confirm that with my calculator. Negative 123 divided by 99. And notice in decimal form it's 1.2424242424, etc. It's not showing you all the digits. They do go forever. And finally, 0.314514. Okay, I do see a repeating pattern. It's a 145. You see that 145 repeats. But the decimal is not immediately next or at the start of the cycle. There's a 0.3 that precedes the repeating part. So again, let's call this an a. And ask yourself first, what would you need to multiply a by to get the decimal to the start of the repeating cycle? And that would be doing 10 times a. Because you want to move the decimal once. So 10 times a is 3.145 repeating. And now, what would you have to do to move this decimal to the start of the next cycle? We'd have to move the decimal 4 times, starting with a. So that's multiplying a by 10,000. 10,000 times a is going to be 3,145.145 repeating. Right, or you can take this answer here and multiply by 1,000 to go to this line. So 10 times 1,000 is 10,000. And I'm going to rearrange these. I'm going to put this down here and do some subtraction. And start first with the 10,000a minus 10a. It's going to be 9,990 a's. And then subtract the two decimals. Well, the 0.145 repeatings will cancel when the subtraction happens. So I just have to do 3,145 divided by 3. Or sorry, subtract 3. That gives me 3,142. And now I just have to divide to get a. A is 3,142 divided by 9,990. Let's test it that this works. 3,142 divided by 9,990. And notice the decimal we get, 0.3, and then 145, 145, 145, etc. You'll notice that the pattern looks like it breaks at the end there, but that's because Desmos is doing some rounding to the nearest digit. It's showing you a rounded digit, a rounded expression. All right, so whenever you have a terminating decimal, it's easy to make it a fraction of integers. When you have a repeating pattern in both these cases, you can see with a little bit of work, we are able to determine how to express that decimal as a fraction of integers. And finally, create a Venn diagram that depicts the relationship between the whole numbers, there should be no n there, between the whole numbers, natural numbers, integers, rational numbers, irrational numbers, and real numbers. There's all these different classifications. We can work largest to the smallest. Let's start with the real numbers. I also want to mention that the real numbers, the symbol for the real numbers is a bold R. And there is no symbol for the irrationals. Every other classification we had a symbol for it. But there is no accepted one for irrational. If I were to start with the smallest set, something like this would be the natural numbers. This is the 1, 2, 3, etc. The whole numbers is a larger set than that. Let me do it this way. So we have the natural numbers, then we're going to go to a larger set with of the whole numbers. An even larger set than that is the integers. Notice we get more and more inclusive. If you divide two integers, you get the rationals. And then finally, the rationals combined with the irrationals make the reals. This is your basic Venn diagram involving 5 of the 6 I say to mention. And the irrationals are the ones in this outer ring. So I'm not going to take the time to shade that well, but the outer ring here represents the set of the irrationals. I'll just put IRR for the irrationals. All right, now remember that the natural numbers were all the counting numbers, so 1, 2, 3, 4, etc. The whole numbers was the same set, but with 0 included. So 0, 1, 2, 3, 4. So anything, I put n is nested inside of w because everything that's a natural number is also a whole number. Well, the integers, the z, was all the whole numbers and their negatives. All right, so if I were to put some examples in these different parts of the Venn diagram, we'd have 1 would be in here, 2 would be in here, 3 would be in here, etc. 0 would be the only example of a number that's outside of n but still inside of w. And then we'd have -1, -2, -3 would be examples of things that are integers that are not whole. The rational numbers, if you recall when we talked about the rational numbers, we did some examples, notice that sometimes when you divide two integers, you get an integer back. In fact, every integer, like 3, can be written as a fraction of two other integers. So in other words, all of the integers are also rational, including 0, right? Because 0 is an integer, and you can express 0 as a fraction of integers as well. So this tells me that everything that's in z is also in q. That's why I put q as containing z. But the things that would be outside z but still inside q would be all the fractions that don't simplify to integers. So I'm going to just do several examples of some fractions that don't simplify to integers. Would be in that ring. Then the irrational ring would be examples of numbers that cannot be expressed as integers. So like square root of 2, square root of 3, pi. There's another number called e, called Euler's constant, would be examples of irrationals. And then the real is pretty much all of this stuff. Everything that is in all of these circles forms the set of real numbers. If I were to do a Venn diagram working from largest set to smallest set, there's a few ways you could do this. You could say, let's do a rectangle for all the real numbers. This stands for all the real numbers. The real numbers are split not necessarily equally, but one side of this would be the Let me move this over. One side of this would be the irrationals, and the other would be the rationals. So you could split the reals into two disjoint sets, the rationals and the irrationals, because you can't be irrational and rational both, by definition. And the rationals, from there, we start getting the nested. So inside the rationals, we would see the integers. Inside the integers, we would see the whole numbers. And inside the whole numbers, we would see the natural numbers. So here's an optional way, if you will, to do a Venn diagram that shows the relationship between all these different classifications of numbers that we've learned. And that wraps up